So we'll start with a new topic today, and this is on momentum. So momentum is a concept which is very closely related to the concept of force and the equation of motion. And the way one defines momentum is, loosely speaking, we can characterize it as the amount of motion present in a system, right? However, anyway, we know that momentum we usually write as v. So this is in the vector equation for momentum, which is basically mass into the velocity, and I can also write it down in terms of let me write down as dr over dt. Right. So this is the equation for momentum, or this is the momentum carried by a particle or the system. Right. And what we can do is, we can also write then with this momentum. Now I can write down the force equation or my equation of motion, and this is then the more accurate form of equation of motion. So, and what it says is that the force applied on a system is equal to rate of change of momentum of that system or that particle. Right? So instead of F equal to ma, we write the more or less the same thing. Of course, there are differences. Force is equal to dp over dt, and if I write it down in terms of velocity, then it's basically v. Right? So this is the actual definition, or this is the actual expression for writing the equation of motion. Force is equal to the rate of change of momentum in a system. Right? Okay. Now, just to make this point slightly more obvious, what we can do is, let's say I have a system with constant mass, right? So I'll say that. So basically, what we are saying is m is a constant. It's not changing with time, right? And then now, if you look at this equation, the way we can now write it down is F equal to d over dt, which is mv. And then, since we are explicitly saying that m is not dependent on time, right? It's a constant. Then we can also take it out, and then it becomes dp over dt, which is your familiar expression, right? So I'll write it as familiar. Right. So effectively that's what we are saying by just writing it in a slightly different term. However, the thing is, it's not necessary that for all systems this mass is a constant in time. Right? There are systems which evolve in terms of their position as well as the mass can change. And in that case, the exact definition or the more accurate definition is that force is equal to the rate of change of momentum, which is governed by both the mass, instantaneous mass, as well as the instantaneous velocity. So one has to be slightly aware of that. So if the mass is constant, if it's given, then yes, we can get force equal to mass into acceleration in that term. If not, then you can write it as general. Right. So the general expression should always be. So we can always start with this point, and of course, if the mass is constant, we can simplify it to our familiar expression. But in general, this is the equation of motion, and of course, in terms of momentum, this is basically simply dp by dt, or we can also write it down as p dot. Right? So this is the equation of motion. Okay. And now what I'll do is, we'll just take an example to sort of discuss this important point. So we'll just take a system where mass actually is changing, and then we'll see what is the effect of changing mass on the evolution of the system. So I am taking this example 4.12. I take this example 4.12 from the book of Klepner and Kolenkov, and the statement of the problem is given here. Right. So now, once you have the statement of the problem, we can try to solve it. Right. And the idea is to find out the force required to keep the motion uniform. Right. So what we can do is, the way I can describe this is, let me first write down the initial momentum at any time t, right? So I want to write down this first, and again for the entire system. So the rocket, which is moving with its own velocity and has some instantaneous mass, and the amount of mass because of dust particles that is going to be accumulated on the rocket at that instant t, right? So we'll write it down as pi at time t is equal to total mass of the rocket. So let us say it's capital M, right? And it's moving with velocity v, plus, let us say in the same time, delta M is the mass of the dust particles, and this is moving with velocity delta u, right? So this is the initial moment of the system, right? So at an instant t, this is my rocket which is moving with certain momentum, and I know that in a short interval t plus delta t, I am going to accumulate something like this amount of momentum, or this amount of momentum is going to be put on the rocket. So this is the initial momentum, right? And now the final momentum. So final momentum Ef at t plus delta t. So in a short interval delta t, what has become is this amount of mass has now accumulated on the rocket, right? And the condition that we want is that the rocket keeps moving with the same velocity. Rocket keeps moving uniformly, right? So basically we are saying that this v does not change, and of course this problem is slightly more involved, which probably you can solve as one of the assignments. However, let's say rocket is moving uniformly. That means in delta t, whatever mass it accumulates, so the mass becomes m, which was the original mass, plus delta m, which is accumulated in time delta t, and now the entire system keeps moving with velocity v, right? So this is how we want to do it. This is what we want to write down. And if this is the case, then all we have to do is find out if there is a difference in momentum, final momentum, initial momentum, and that will give us the force, right? Because force is the rate of change of momentum, right? So we can write down delta p as pf minus pi. So this will be mv plus so m plus delta m v minus mv minus delta m u. So this is the case, and now this will cancel out. Delta mv, delta mv, this gives us v minus u delta m, right? So this is delta p, right? And we know that this is in time interval delta t, this change in momentum. So I can divide both sides by delta t, and then so I will get delta p over delta t is v minus u delta m over delta t in the limit delta t tends to 0. So in a very, very short interval, right? So same limit on this side. This will become dp over dt, right? Which is nothing but the force required, and this will then you can write down as dm over dt, and this is given that the rate of change of mass or the rate of accumulation of mass is dm over dt. So we can find out the force as v minus u dm over dt, right? So this is the force. So now you can see that the force has an effect of the change in mass. It's not just the change in velocity, and that's just a problem to demonstrate how this affects different systems. So of course you can go through these various examples given in the book and get familiar with this kind of understanding. Okay. Now next what we can do is, we can also write down this equation f equal to dp over dt, right, in an integral form, and what we can say is, we can say p2 minus p1, so basically integrate on both sides, is equal to integral f dt from t1 to t2, right? So that's the integral form of the same thing. So if we integrate force over time, we get the change in momentum, right? And this expression, integral of f over f dt, is now termed as impulse, right? And this is, and if you look at the force, if you look at the same equation of motion in a slightly different way, it does convey some extra information, and what then the information that it conveys is the change in momentum, let's say between the initial and final state, right, is an integral of force over that time, the time that it takes to change the momentum, right? So effectively, the change in momentum then depends on the average force, right, applied over a given interval of time. It basically is not really dependent on the nature of the force or the characteristic of the force. It simply depends on this integral f dt, right? And to demonstrate this in slightly more clearer terms, basically what this equation says is, so let's say if we can plot f of t versus t, so this is the force and this is the time, right? And now we can have different types of forces acting on the same system. So for example, there could be one force which looks like this. So basically you start at t1, you end at t2, right? And this is my well, some value, I'll call it f1, right? So the system is no force, suddenly there is a force on the system, and then after time t2 again there is no force, and there is some response to this, right? Now we can also have something like this, working to t3. So then this becomes my second force. I can also have a force applied on the system, on the same system, like this, where then this is my f2, right? And then this f2 is now applied from t1 up to t3, right? However, the value of f2 is much less than the value of f1, right? That makes a different force. We can also have something more complicated, right? For example, we can have something like this. Let's say start from here, go up to here, and come back here. This is f3. Right? So there are different kinds of forces applied on the system, right, over different levels of time. However, what the expression says is, as long as this quantity is same for the different forces, the result will be same. The change in momentum will be exactly the same, right? So graphically, what that means is, as long as the area under these curves, right, and similarly under this curve, as long as the area under these curves, so basically, so what we can say is integral t1 t2 f1 dt is same as integral t1 t2 f3 dt is same as integral t1 t3 f2 dt, right? This is basically going to give me the same delta p, or the same effect on the system, right? So it doesn't matter how you apply the force and for how long and all that. We can have different kinds of forces, or not as much as in character, but basically either more intense or less intense, or a different time variation of the same of the force. Nevertheless, as long as this integral is same, the effect will be exactly the same, right? So that's the importance of impulse. And so okay. And now what we can also write down is, we can also write down this quantity within some time interval dt as then f average over a characteristic time, right? Something like this. So in the sense that one can forget about the time behavior of the actual force applied and replace it with an average force over a characteristic time interval, right? Which is going to be given same as this quantity. Okay. So let's now look at this again in terms of an example, and where this is useful is in finding out the force or the effect of force due to a stream of particles for example water jet, air jet, right? Or well, there's an example given in the book which deals with photons, right? So we can solve the problem just by using the impulse, and I'll demonstrate one of the cases here, right? So let's do that. So again, what we are saying is, so let's say there's a problem given, something like this. I have a wall, right? And I have a stream of particles. So let's say you take a normal toy gun, right, and keep on hitting with the bullets on the wall, right? And you want to see if I fire it continuously, what is the average force seen by the, or what is the average force seen by the wall, right? And it's the same problem as if I take a water hose and point it at somebody, and then if I continuously hit him with the force of water, then what is the average force that he is going to feel? Okay. So something like that. So let's say I have a stream of particles 1, 2, 3, 4, which are all moving in the same direction with velocity v, hitting this wall, right? And for time being, we'll consider that after hitting the wall, they don't recoil back. There is no elastic collision. They don't come back. They simply fall down, right? So they lose all the momentum in the ball. Okay. So if that is the case, then we can write down for this, let's say, again, initial momentum, and that is going to be equal to mv, where m is the mass of each of this ball or droplet or whatever you want to call it, right? Each particle. So m is the mass of each particle. Final momentum is 0, right? So now I can write down the force. So what is the force? So well, first of all, delta P is minus mv, right? So this is the momentum change of the droplet, right? And this same as the impulse, right? We wrote down that integral equation. So this is also equal to the impulse given by each drop, right? So the impulse on the wall due to each drop or ball, I don't know, doesn't matter, is then we can write it down as, well, we write it as f dt, right, general expression, and this is equal to, well, if the impulse given by the drops on the wall is minus mv, then this is going to be the negative of that action. Every action has equal and opposite reaction. So this is the impulse given by each droplet, right, or each ball on the wall. Right. Now since a continuous stream, right, we'll make some more assumptions. In the sense that we'll say that the balls or the drops are coming at a uniform rate, right. So in that sense, if we so the way we can write it down is I'll also say average time between each ball or drop, right. So the average time interval between each ball or drop is t, right. Then what happens is, physically if you see, a ball hits here, transfers momentum mv, and then for time capital T there is nothing, right. So of course this time of one ball hitting this and transferring all the momentum can be very, very small. That's your dt, right? And the way the force is going to change, we don't know. We are not interested in those characteristics. However, we know that once this much momentum has been transferred, there is a time t for which nothing else happens, and then the same quantum momentum gets transferred again, and that's why we are using this integral equation, because then now we can average out the behavior of the system in this entire time t with some average force, right? So what that means is, let's say there is an average force. This is the average force felt in this time t, right, between two collisions. This is going to be same as the instantaneous force applied by the one ball over a very short interval time t, the impulse, which we already know is equal to m of v, right? So then this is the average force. And now I can write down this average force as mv over t, where t is the time interval between different collisions, right? And now what we can replace t in the sense that we can say that if the average distance between individual droplets is L, then I can change t in terms of v L over v, right? So basically this L is nothing but Vd, right? Because each droplet is moving with velocity v. So F average is mv square over L. This is an expression for something like this. Okay. Now why have we written it like this? Is because now what I can do is I can convert this system into a more continuous system. So let's say stream of water, where normally you are not going to see it as droplets hitting. You are just going to see it as a mass of water hitting uniformly on the surface. So let's say this is my surface, right? And now what I can do is I can say that let's say I have a continuous distribution of any particle. This could be balls or water or air particles or whatever, right? It's there. And now looking at the same problem, we know that in a unit time, if the stream is moving with velocity v, right, then in unit time, L is the column or the length of the mass that is going to move, right? And that time we got from here to here. There was a difference between this was the time between two collisions, right? And the total mass contained was m between these two collisions. So now this mass is distributed. It's a continuous stream. So this mass is distributed over this entire length. Let us say A is the area of cross section of this column. We can assume it is cylindrical one, right? So then what I can do is I can extend this, right? I can write rho is the mass density, right? So for example, the water density. If it's oil, then oil density, right? So now what I can do is I can write down from here m over L as rho into A, right? Because m is the mass of the column, rho is the density, right? L is the length, A is the area of cross section. So we know that the total volume is AL, and m over AL is going to be rho. So I can replace this by rho, so that we don't have to worry about these different factors, right? Because you are not going to measure what is the actual length of the column and all. So, and in that case, F, which is average, right? F average is equal to, so M over L, so rho V square A. So we can also write down for a continuous stream of particles the average force as this, which now basically depends on the density of the system, the velocity with which it's moving, right? So the water goes, and the area of cross section, right? So we are not worried how far the droplets are separated. Should we go to the approximation of droplets, and then is the collision elastic and all that? I mean, of course, we are considering that nothing gets recoiled, right? The water is not reflecting back, right? But in that case, then we have simplified this problem in terms of the known parameters: density, velocity, and area of cross section, right? Okay. Now, so this is as far as we need to solve this kind of problem. For example, with this similar approach, we can find out the pressure because of air in a closed container, right? Because it's nothing but the air molecules hitting the walls of the container, right, and transferring certain momentum. Of course, there we take the approximation that the collisions are elastic. So instead of transferring momentum mv, they actually transfer momentum 2mv, because the particles are moving with velocity mv, hit the wall, and then come back, right? So try this problem. It's also solved in your book, right? So however, we can write it down like this, and of course, what we can do is we can write it down more accurately as a vector equation, because we know that any force is a vector force. So F is rho v square A, and of course in the direction of motion, right? So we can, so for time being, I take this direction as v cap, right? So that's unit vector, unit velocity vector describing the direction. So rho v square A, right? Okay. So this is my equation for a continuous stream, and slightly some more details about the equation, which I'll simply mention here, and because probably we don't need them much in the during this course, right? However, just to complete the topic, this quantity rho v square, right, is also written as capital J, right, and termed as the flux density, right? So it kind of relates to a current, right? There's a mass, there's a motion, so it's called the flux density. Of course, what we can also do is we can look at this equation. Average force is mv square over L, right? And we can see that this is nothing but momentum transferring per unit time, right? So for example, if I slightly change my problem and say that now instead of a wall, I take this as a virtual plane or an arbitrary plane, right? And I say that in unit time, some mass is flowing with velocity v across this plane with the cross-sectional area A, then effectively this is same as saying that momentum mv is flowing through that cross-sectional area in time t, right? So it's a momentum, for transport of momentum or momentum flow, I'll write it down as momentum flow per unit time. Right? So you can just see this from dimensional analysis also, just mv over t. So it's a momentum flow per unit time. But this kind of discussion helps when we are looking at a continuous stream of particles, where we cannot actually see the force applied due to individual particles, right? So that's this thing. So it's related to this flux density, right? And then the equation can also be written as well. So average, yeah, it always remains like this. So this is also equal to your P dot, right? We know that the rate of change of momentum is J, which again will be a vector quantity, and then its dot product is taken with area, right? This area, and now this area is also a vector quantity. So in general, so I don't know if you have not heard it earlier. Let's introduce this here, right? For time being, just as a statement, that area is also a vector quantity, right? So area, which is basically length into breadth, or multiplication of two dimensions, the two lengths, is also a vector quantity. So area vector, and its direction is normal to the plane, right? So area basically defines a plane, and the area vector has the magnitude of the area, the normal L square, and the direction is normal to the plane. So in this case, this n cap vector will define the area vector. So the average force, rate of change of momentum, right? And now this will also be called momentum flux, is flux density into the area. So flux passing through unit area over that area, and in the direction of the vector, the velocity vector, or the direction of the motion of the system. Okay, so let's leave it here. We don't have to dwell much on this right away. Right. However, what is important is to understand this analysis, and then you can probably try to apply this to find out the average pressure because of air inside a closed container, on the walls of the container, and things like that. Okay. Okay. So we'll continue further on the momentum in the next lecture.